Lesson 14, coordinate proof. Our aim today is let's use our knowledge that's not spelled right, of slope and distance to prove shapes are specific quadrilaterals. All right, so 14.1, which one doesn't belong? Coordinate quadrilaterals. Which one does not belong? So what I'd like you to do first is pick one of these four shapes, A, B, C, or D, and explain why you think one of those four does not belong with the rest. So, hopefully you recognize some familiar quadrilaterals from earlier in the year. And all of these quadrilaterals actually fall under the larger family of parallelograms. All right, and if you remember, we have 5 different ways that we can prove a quadrilateral is a parallelogram. All right, number 1, both opposite sides are parallel. 2, both opposite sides are congruent, meaning they have the same distance. 3, one pair of opposite sides are parallel and congruent. All right, 4 and 5, congruent or diagonals, not congruent, diagonals bisect each other. And number 5, both opposite angles are congruent. So we're going to use our knowledge of slope and distance, the stuff that we've been working on the past few lessons, to try and get some of these proofs. So out of these 5, 4 and 5, we really are not going to be proving using that, because we know how to prove things are parallel, and we know how to prove 2 things are congruent. All right, to prove things are parallel, we find out that they have the same slope. So we're looking for change in y over change in x. For example, if I'm looking right here, CD, I can see my slope is up 2 over 2. So the slope is 2 over 2, or 1. Then I can see that AB is also up 2 over 2, or over 2 up 2. So that slope is equal to 2 over 2, or 1. So these 2 sides we can say are parallel. Same with these sides here. I can say down 2 over 2. So it's negative 2 over 2. That's equal to negative 1. Or really negative 1. Here we've got down 2 over 2 as well, which you know is the same slope. So we know that these sides are parallel. When we're talking about things being perpendicular, all right, we want one slope to be A over B, and the other to be negative B over A. And if we look at these opposite slopes, or these slopes here, the adjacent sides, I've got 2 over 2 and negative 2 over 2, which are negated reciprocals. So not only do we know opposite sides are parallel, we also know that adjacent sides are perpendicular. We also want to find the length of sides. It's pretty easy here in this shape, right? This square right here, it's 2, 2, 2, 2. We can just count the boxes. However, when sides are diagonal, it gets a little trickier. All right, but you have a method of finding diagonal sides like this. And to do that, we create a right triangle. So I know this side is 2, I know this side is 1, and these are the 2 legs. We can also call this leg, since it's the vertical direction, our change in y. And then this would be the change in x. And then this will be our c, or really our distance. So if I'm using the Pythagorean theorem to find distance, I'm modeling it off of a squared plus b squared equals c squared. But if I want to use terminology that's more like what I'm seeing on a graph, I can write change in x squared plus change in y squared equals d squared, where this d represents distance. All right, so there's lots of things we can prove in this coordinate plane. So very important that we know these 3 different ways. All right, whatever is easy for you. If you like finding slope, if you prefer finding distance using the Pythagorean theorem, find one way that works best for you. We also need to go over the individual shapes here. All right, we have a different types of parallelograms, right? We have square. We have, actually, I don't want to start off with square. I want to start off with rectangle. Then we've got rhombus. And then we've got square. And you'll see why I put square last in a second. So if you remember from our quadrilateral unit, once we know a shape is a parallelogram, we want to use the minimum information we can to show it's not just a parallelogram, it's also a more specific quadrilateral. So for a rectangle, all we need that it's a parallelogram, and then that we have one right angle. So to prove that, we would show that adjacent sides, one pair, adjacent sides are perpendicular. For a rhombus, we know that adjacent sides are congruent. So one pair adjacent side. So it's always important to think about these things when you're proving something, right? If you know you need to show it's a rectangle, it's better off in your proof for a parallelogram to find all the slopes, because you're going to have to find slope eventually to show that they're perpendicular. If you're trying to prove something is a rhombus, you know you're going to eventually have to prove that adjacent sides are congruent. So maybe you use this method here, number 2, to prove that it's a parallelogram, because you know you're going to have to find the distance eventually. If you get a square now, you're going to have to do a little bit of everything, because a square is kind of like a combination of a rhombus and rectangle, in that you've got one pair adjacent side perpendicular and congruent. So you got to do both of those 2 things. All right, that's all for 14.1.